Thank you again for the honor to speak before you today, and I am delighted to share with you new trends in numerical modeling of seismic soil structure interaction. The work that I'll be describing today is the product of many collaborations with colleagues at other universities, as well as several of my master's and PhD students, and I've really acknowledged their efforts in this regard. I'll first share with you the motivation for the problem, why we're interested in this issue of seismic soil structure interaction modeling, describe some of the current state of practice methods, highlight a few aspects and considerations for modeling, and then I will provide you with some example developments and applications focusing on material constitutive modeling and computational considerations, and then demonstrate to you the application of these tools for 5 problems. And then I'll wrap it up with some conclusions and engineering implications. Why are we interested in this? We have our physical infrastructure is the backbone of modern society. We're interested in understanding its performance and resilience under extreme events. In this particular case, we're interested in its performance under earthquake shaking. We are dealing with high-rise buildings, underground structures, deep foundations, bridges, piers, and all of these end up interacting with the surrounding ground and next to each other. And we need to understand how these interactions impact the overall performance of our infrastructure. We're interested in this because we have seen damage to our infrastructure with sometimes serious or severe consequences. Here we are looking at significant settlement at the Kashiwazaki nuclear power plant in Japan. These settlements led to damage to utility lines and shutdown of the nuclear power plant. You're looking here at bearing capacity failure of buildings due to liquefaction during the Kocaeli earthquake in Turkey. This is a damage of a buried reservoir, water reservoir after an earthquake. This is damage to a subway station in Kobe, Japan, due to this significant earthquake that happened there in 1995. This is an example of a building in Los Angeles where there's a significant earthquake hazard next to tunnels, stations and tunnels, and we're interested in understanding the interaction between these buildings and tunnels. And this is a damage to a concrete face rockfill dam, and specifically the joints of this dam after the 2008 Wanchuan earthquake. So our infrastructure is experiencing damage, and we are interested in understanding how these interactions are impacting the performance, the damage, so that we can design and build to mitigate these issues. So now let's talk about sampling of state-of-the-practice modeling methods that are available to us as engineers to address these problems. Well, we have a number of simplified methods. For example, for soils, we have some simplified methods to estimate strain due to seismic shaking of sands, and from that we can estimate settlements. But this is decoupled from the superstructure that is, for example, placed on top of the sand. Liquefaction procedures, these are widely used, for example, procedures by Idris and Boulanger, and we use them to evaluate whether soil is likely to experience liquefaction or not. But this is only focusing on the soil itself. There is no interaction here with the structure. These are some methods we developed for looking at the seismic interaction of underground structures. They are simplified. We apply racking displacements, and depending on the relative stiffness, we are able to estimate the deformations of the structure. But these methods are predicated on relatively small strains and elastic response of structure. So we do not have in it the ability to incorporate the nonlinearity using these simplified methods. We need to do more. Codes are rich with procedures for evaluating structural response, all the way from starting from a fixed base model to a complete system where you have a complete soil structure interaction model. But nevertheless, the best way to do that in trying to use these simplified spring and dashboard methods is difficult, cumbersome, and often fraught with uncertainties due to our inability to characterize well these springs, for example. So we need to model everything together, and that is really why we need to move into a full modeling of the soil structure interaction to capture the behavior of interest to us. So now let's talk about what are the elements, the ingredients that we need to be able to conduct this type of modeling. We need to represent the soil, we need to represent the structure, we need to represent the ground motion. In order to do an adequate soil structure interaction analysis, it is important that we do detailed site investigation whereby we characterize the ground and understand the stratigraphy and the soil properties of interest. When dealing with seismic soil structure interaction, the number one property we want to capture or measure is the shear wave velocity, and a direct measure of the shear wave velocity is essential. This is, for example, using the OYO suspension logger. We have developed a soil profile of the shear wave velocity and the P wave velocity as well. Now, why is the shear wave velocity important? Because it represents the maximum stiffness of the soil. The shear modulus is equal to rho times Vs squared, Vs being the shear wave velocity, so it's critical. There is much more to say about the importance of site characterization, but it is beyond the scope of today's presentation. In order to conduct a seismic soil structure interaction, it's important to represent the ground motion that is going to cause the shaking that we are interested in representing. And there are many steps that one needs to take to develop those ground motion, conducting probabilistic and deterministic seismic hazard analysis, developing target spectra. It could be uniform hazard spectrum, it could be conditional mean spectrum. And then after that, we have to develop time series that match the response spectra. And the selection of these time series, both horizontal components and the vertical component, is a significant effort. It's very important. It's essential for a successful and meaningful seismic site response analysis. However, this is beyond the scope of today's discussion. Now, when we are thinking about seismic soil structure interaction and modeling, we want to think of a series of models, a sequence of modeling instead of a single analysis. First, we need to make sure we have a good handle on one-dimensional site response analysis. You can use tools like deep soil shake. You can also assess liquefaction in the free field, just to make sure you understand what's going on at the site without the presence of structures. Then we can start looking at introducing elements of the structures, tunnels, tall buildings, nuclear power plants, for example. These are very heavy structures. And then we have to look at now, so these first we do them individually. We analyze the tunnel by itself, building by itself, a power plant by itself. Then we start looking at the interaction between these structure to structure interaction. In this particular case here, we are looking at a structure to a tall building to an underground structure interaction. And here we have other examples of interactions. Now we're looking at a buried reservoir where we have to deal with the interaction of the soil, the structure, and the fluid, or a dam where we have to deal with the structure, the soil, and the fluid. So it's not just about a structure and a soil interaction, it's a structure-soil-structure interaction, or a structure-fluid-soil interaction, depending on the problem. And we are in an era where we can represent those interactions explicitly. In terms of analysis tools that are available to us, we have a number of analysis platforms. And I'm focusing mostly on commercial platforms that are accessible to both researchers and engineers. You have FLAC, Plaxis, RS2, LS-DYNA, OpenSeas, Mastodon, Abacus, Adena. There are many available platforms for the analysis. From a geotechnical point of view, we often work with FLAC and Plaxis, whereby we can represent well the soil, but the structure we often have to pay a penalty, and we have to simplify the representation of structure. In other software platforms, Abacus, Adena, OpenSeas, and LS-DYNA, one can have a higher fidelity representation of the structure and a good fidelity representation of the soil. In today's presentation, I'll focus on the use of Elastina, being quite a versatile platform that we have used both in research and in engineering practice. There's a need, of course, to represent the structure and constitutive models for the structure, but of a significant importance is the representation of the soil constitutive model, and that is often something that we need to pay particular attention. In Elastina, there is a material called MAT79. I will describe it a little bit more as we talk about the modeling developments. PDMY02 is available in OpenSeas. It's mostly calibrated for liquefaction. It has macing type unloading, reloading, and it is a bit challenging to represent both modulus reduction and damping simultaneously in it. In FLAC, we have the HS small model. We have also PM4SEN and SILT, and this allows us to represent some problems. And then in FLAC, there are a number of models, including UBC-SAND for representation of hardening, elastic unloading, reloading, and a number of features. Different platforms have different strengths and weaknesses, especially when it comes to working with very large problems. And for that purpose, for that reason, we have chosen to focus on our work and what I'm going to be presenting to you today within the platform Elastina. In terms of the structural modeling, we can model it either as a rigid structure. We're only representing, therefore, the inertia as opposed to the modes that may be contributing to the structural response. It can have lumped masses or frames composed of beam and shell elements, or a complete 3D structure, solid elements. It is often a problem and platform dependent. And the material can be linear elastic or nonlinear. And depending on the severity of the shaking, you may need to be working with nonlinear representation of the structural response as well. Interface conditions are always challenging, and there are a number of tools we can represent as a full slip, no slip, and something in between. And often enough, it is actually something in between because it represents the real world conditions. The modeling can be 2D or 3D. So we have, depends on the problem we have. This figure here shows you some of the work we have done. This is way back in 1998 to look at the interaction of an immersed tube tunnel with the surrounding soil. We were able to represent a number of geometric and soil complexities and the interactions. Here, in this figure, we're looking at the interaction of a simplified representation of a building and a tunnel. While in the 1990s, it was quite cumbersome to even run a dynamic analysis in 2D. Nowadays, we are seeing increasingly and common use of three-dimensional soil structure interaction, and that is the trend we are increasingly seeing in both research and practice. So what are the gaps and the needs that motivated the work that we have done over the last now almost 7 or 8 years in this area? What are the gaps in numerical modeling and material constitutive modeling? We need an analysis platform that can have higher fidelity representation of both the structure and the soil, as well as the interface. If you want to do high fidelity soil structure interaction, you cannot represent the structure as a simple pendulum, nor can you represent the soil as a mere spring. You need to explicitly represent both. We need to be able to capture the 3D geometries because they play an important role given the three-dimensional nature of the excitation, the ground shaking. We have structure-specific interactions, complex geometry, soil settlement, and also soil failure, including liquefaction. We're interested in performance-based design, so therefore we need to understand how all of these work together. And we will need to be able to run these simulations efficiently, and we need to capture uncertainty. So therefore we need to run many of these simulations. So we need to be very mindful of computational cost. We're not looking at one simulation we're looking at multiple simulations. So now I'm going to share with you the developments and applications in this area that we have performed. I'll talk about constitutive modeling. I'll give you, as I mentioned, examples of 5 applications, and then we'll give you a discussion of computational considerations. So let's talk about first advances in soil constitutive modeling. When we started this effort a number of years back, we wanted a platform that is quite versatile and computationally efficient, and that was LS-DYNA. But we needed to have a material constitutive model that is robust and captures important features of soil response. And it was really motivated by the problem of looking at settlement of heavy structures on dense sands. This was supported by the US Nuclear Regulatory Commission. So if we look at a conceptual constitutive model for seismic behavior of sand, we need to represent the unload-reload behavior during cyclic loading. If we look at the backbone curve, we need to represent the modulus reduction with increasing shear strain, and we need to represent the increase in damping energy absorption, which actually represents these hysteresis loops with strain. So we need to represent small strain stiffness, which is the measurement of shear wave velocity. We need to have an idea about this normalized secant modulus reduction curve, and we need to represent hysteretic damping, which is non-macing, and that is important to be able to represent it. And fourth, we need to represent shear-induced volumetric response. This is when we have a drained response where the water can dissipate and the sand can settle. In situations where these cannot happen, we need to develop the corresponding excess water pressures. So we developed at the University of Illinois as part of the PhD thesis of Ozgun Norman-Oglu, and he's now graduated and working in industry. And we were looking at extending an existing soil model, MAT79, in LS-DYNA, which is based on distributed element plasticity model that was introduced by Xiang and Beck in 1994, and it was based on the Iwan 1969 model. And the reason we picked this model because it is simple, elegant, and easy to implement and easy to extend. The model formulation is a piecewise linearized hysteretic non-macing type nonlinear model, can represent modulus reduction and damping curves. The model it represents the shear-induced volumetric strains and excess power pressures. This is the ISOL extension of MAT79. And initially, we used it to represent medium-dense to very dense sand behavior, but it's proving to be very promising for loose to medium sands. It's easy to calibrate and use. We use the analysis platform LS-DYNA. What we did not include was plasticity due to hydrostatic loading and isotropy critical state behavior. Why did we choose LS-DYNA? It was designed as a framework to solve dynamic problems. It provides detailed representation of structural components, fluid modeling capability, ease of use. It has a good, nice graphical user interface. It's computationally very efficient. It has parallel computing capabilities, so it can run on a PC, it can run on a server, it can run on HPC, high performance computing system, and it's easy to automate and queue the analyses. It's really a very simple, elegant model in a one-dimensional frame. If we think about it in a one-dimensional framework, and then you have to think about extension in 3 dimensions. It's a simple spring slider system, elastic, perfectly plastic behavior, and it produces macing type hysteretic behavior upon unloading, reloading. And then once you put several of them together, you superpose them in parallel, and you can with that you can represent the stress strain behavior of the soil. You can have components 1 to n, and is equal to 4 here for demonstration purposes. And it's a piecewise linear. To be able to represent the a smoother transition, you add more sliders, more springs and sliders, and it's pretty simple, straightforward. It may seem computationally expensive, it is not. And it allows us to represent the normalized modulus reduction curves. We also added to the model, as part of our development in iSoil, 2 parameters for volumetric response calibration. And this is a plot of how we've calibrated it. We plotted confining stress versus deviatoric stress versus confining stress for a number of tests. And we developed a range of this eta DSR, and it implies it has an implication for a friction angle, which remains reasonable and consistent with established empirical correlations. Another parameter is A0 for which is a trial and error model to allow us to properly represent the degradation in the stiffness of the soil, meaning the reduction in the stiffness with repeated number of cycles, and with that also it represents the settlement or pore pressure generation. In this case, what we're looking at is RU versus shear strain, and you're seeing the increase in pore pressures upon continuous cycling of the soil. And we find that A0 of 0.5, for example, here is capturing well this test. Cycle 1, cycle 2, cycle 3. And so once you put them all together, we compare them. We compare the performance of the model to a number of tests. This is from Sibley 2016, and we are seeing quite a good correspondence between the measurements, which are in red, versus the blue, which is the model. We're looking at also pore pressure generation, and here we're showing the residual, and we're doing a pretty good job here capturing the measured behavior. Now, there are a number of parameters that this model requires, and that's often a vexing problem for people. It's like, look how many parameters you need. That is true, but the reality of it is these can be simplified significantly. For all the parameters we have, all of them can be obtained from the modulus reduction and damping curves that we are commonly use in 1D nonlinear site response analysis. There are only two volumetric parameters, A0 and eta DSR, that we calibrate using cyclic DSS or empirical correlations. We have recommendations in the thesis of Dr. Noman Oglu, but also if you have your own tests, you can also calibrate these. So in reality, we only need modulus reduction, damping curves, and these two parameters, A0 and eta DSR. Very straightforward calibration of the model, and that was we tried to keep it as simple as possible. So now let me show you examples of the performance of this model. This is first application, which was the original intended use of this soil model, is to look at the settlement of heavy structures on dense sand. We conducted a series of centrifuge experiments, bidirectional, so you can move in two directions. And we placed a heavy structure representing a nuclear power plant, and we conducted both free field and experiments with the structure on it, and we shook it so that we can see accelerations, displacements, and settlements throughout the soil column. And in doing the modeling for these experiments, we did one-dimensional models, then we did shear beam representation in Alastaina, and then we did the full three-dimensional model, whereby the structure was simply represented as a rigid steel cylinder. And this is an example of the comparisons we had between the measurements and the and the computed result. So blue is computed in deep soil. This is a free field. Then we have the black, which is the Alastaina result. Then orange color is measured, and the dashed line is input. So if we look at the surface here, and the first column is x direction and y direction. So we shook the structure in two directions, two horizontal directions. And if we look at this, for example, we find that this is the input, so that's not what we're comparing. We're making sure that the input is the same, and then we look at the output. And you can see here that when we are modeling the soil structure interaction, we are representing the observations very well. We're looking at the response spectral acceleration. We're capturing it well across a broad range of periods. We're able to capture the area's intensity and the Hausner intensity well, the development of that. And these are the settlements. It's showing us the trends of the settlements that we are observing and the generation of pore water pressure. We did not try to over-calibrate this. What we had a series of tests in the lab that we used to calibrate the soil model and then use them in a predictive manner to represent the soil structure interaction. So we wanted to see, can we be anywhere in the vicinity of these numbers? And we are doing quite well there. Another thing we're interested in is computed versus measured settlements, and this is a 2-to-1. And we find that when we look at the residuals, we're actually hovering around 0, which is pretty encouraging. There are other techniques we use, the simplified methods versus the blue, which is the 3D SSI, and you can see the 3D SSI model residuals, which is a residual, I should mention, is the relative error between the measurement and the computed value. The blue data represents the soil structure interaction, black represents modified empirical relationships. When we do the seismic soil structure interaction, we're doing a much better job capturing the behavior. 1-to-1 gives you a perfect match. We're hovering around that. And so we are doing quite well there when we are using the multidimensional SSI simulations. So we said, okay, so this thing worked well for an idealized nuclear power plant. Let's work with a real one, the Kashiwazaki nuclear power plant in Japan, which experienced significant settlements and damage, and it led to shutdown. And so we said, well, how about we try that one? And there we're dealing with uncertainties with real measurements, real data, but that's what you want to do. First, we did it under control conditions, centrifuge experiments where we have a lot of control over the test. Now let's see under real world conditions, how does the model perform? So this is the site that we're looking at. This is an aerial photo. This is a site service hall where they've experienced 15 centimeters of settlement due to seismic shaking. And then we have at the site of at this site here, we had about 10 to 30 centimeters. And then unit 1, they had a rupture of the water pipes. And this is all due to relative settlements. So they had when you rupture water, you can have fire, and that can be very problematic. So we have a free field ground subsidence at service hall. We have estimates of differential settlements at unit 1 reactor building, and we have differential settlements at unit 3. And then, of course, that led to temporary shutdown for survey and maintenance. The objective of our study was to utilize ISOL in Alasdaina and evaluate these seismic settlements. So we represented the structure, the ground, and the model, and then we had to identify appropriate input motions at depth, and then we represented by proxy the location of either free field conditions or the building reactor or the turbine building. So we represented all of those to look at the performance in each case. We ended up with 247,000 elements or 225,000 elements, depending on the unit. We used 4 physical cores and 4 logical cores. It took us about 15 hours in this case and 23 hours in this case. And by the way, this is for a problem that is that complex, that large. This is not bad. This was on a PC. It's a server with multiple cores. And then we computed the settlements. Of course, from the site, we didn't have estimates of settlements with time. We only had the final settlements and the uncertainty in it, and here for this building as well. And we came up with values that are within the observed settlements. And so we were quite encouraged that this representation of seismic soil structure interaction did provide measures of settlement that are consistent with what was observed. By the way, we're not looking for exact. If we are there within the right order of magnitude, we are doing quite well. And we are quite happy that this is the case here. Another problem that we had to deal with, and this actually started from a real-life project, is we have often now in major cities, we have high-rises that are built next to deep underground stations or tunnels. And all the design methods for the high-rises assume there's a free field around you, and for tunnels assumes there is also a free field. They don't account for the interaction. But if you think about it, when we design tall buildings, we're interested in the base shear. This is the inertial load that's shed into the ground. Well, where does that inertial load go? Does it stop at the boundary of the building? Probably not. It does not. And so now if I put a tunnel next to it, what happens to the tunnel? How do I estimate the forces from the building? Do I just simply put the forces as is? Do I always assume an increase? So we needed to answer those questions, and that was a non-trivial problem for us to deal with. So what we did is we embarked on a simplified way to deal with the problem. We wanted to study it. We looked at a simple representation of the building and said, okay, does it increase earth pressures? How much? Is it Mononobe or Kabi earth pressures? Which, by the way, they don't work for most applications. So that was the purpose to say, well, this is a real seismic soil structure interaction problem. How do we solve it? We need to solve it. So we know that underground structures will will move approximately with the ground. Not exactly the same, approximately. But now I have the structure next to them. What happens? So for that, we conducted a very large study coupled with a major centrifuge experiment work that we've done, whereby we put an idealization of a structure and a tunnel. We performed free field analysis and simulations and experiments, and then one with a mid-rise building and one with a high-rise building. We had to idealize it in the centrifuge because we had limitations in the height that we can put. So for the mid-rise building, we can only capture 3 modes in the simulations. For the high-rise building, we can only represent 1 mode. And of course, you say, this is not necessarily realistic. I understand, but we needed to start somewhere. So we built models. We had the centrifuge experiments, and they were not easy to build, that we conducted in collaboration with Professor Dashti at CU Boulder. And then we conducted the simulations. And we had fairly large models that here we're looking at 25,000 elements with 4-hour runs, or here 26,000 elements, 2-hour run. And then we looked at, for example, the increase in thrust. We had to look at the free field condition, meaning there is no building, what kind of dynamic increment we have. And then we looked at, is there much increase? When you look at the mid-rise building, there's a little bit increase, not a lot. But for the high-rise building, we do see a significant increase. And that has serious implications, because usually the group that builds the tunnel is not the same group that designs and builds the high-rise building. And they really, when they're building, for example, a tall building, they're not thinking, oh, in the future there will be a tunnel. Or when someone builds a tunnel, they don't think that in the future there will be a building. There are some very, very serious implications of these issues that we need to pay attention to, because they do impact and they do result. For example, here, the top part of the tunnel, we can have the excavation, we have significant increase in that. So we're seeing maximum at the top, which is not surprising. Now, currently, we are conducting simulations with far more realistic representations of the building here, with all their modes. We're not dealing with just the simplified models that we had to deal with in our centrifuge experiments. We are looking at more realistic deep foundations, more realistic soil profiles, and we're looking at the impact of how far the building is relative to the underground structure. We're working on those. The simulations we're doing, it's 11,000 nonlinear simulations to better understand the uncertainties and the impacts of these interactions. So now we looked at settlement of a heavy structure, both under idealized conditions and real-world conditions. We looked at simulations of building-tunnel interaction. Another issue for us was, how well does our model represent liquefaction, because we are interested in soil structure interaction within a liquefaction kind of environment. And for that, we used the vertical array at Port Island, and this is in collaboration with Professor Idris. This is Port Island. It's a fill island in Kobe, Japan, and they had a vertical array with measurements, and we had these measurements at various depths, and then we use this input material and then the soil column to try to estimate what the surface computed surface response will be. And we actually found that we are able to represent the observations, and we are able to see the onset of liquefaction when we start seeing the development of long period response. This is digging in a little bit deeper to look at the stress path and the development of this dilation spikes that you often see. We don't have measurements of those, but I'm just sharing these with you to show that we are representing behavior that appears to be reasonable and realistic. So we took that and we now are applying it to LEAP centrifuge experiments, and there's a far broader set of experiments that we are also doing a comparison with. This would be part of Mr. Guang Chao Singh's PhD thesis. And these sleep experiments were centrifuge experiments of a sloping ground with water that's been performed in the centrifuge, and they were performed at different institutions. And we developed the soil column for it, shear wave velocity, relative density, vertical effective stresses friction angle. This is the model that they're working with. And then we represented that in Alastina. Both were able to represent the fluid. Here we represented really the fluid as an elastic element as opposed to something a bit more advanced, which I will highlight in a minute. And then we did a comparison between measurements, which is the line in black, and then we have 1D shear beam model, 2D slope model, and 3D model, no gap. And as we increase the fidelity of the model, we get closer and closer to the observed behavior. We're showing here the stress paths, but mind you, we don't have measurements to compare it with, but we want to see the difference in the behavior. But we're able to capture the buildup in pole pressure, which is really important, as well as the response spectra are quite reasonable and representative of what was measured. Now we'll take you to another problem, which is a water-filled concrete-faced rock-filled dam, and this is based on a series of experiments that the late Professor Kim from KAIST shared with us, and we're really grateful for his generosity in sharing with data, and we were very, very saddened to hear about his passing. The problem is we have, this is a fluid soil structure interaction problem, and we were looking at the interaction of the rock-fill dam, the concrete face, and the water behind it. And there are a number of cases of dam failure that were recorded, which has some severe consequences, and they could potentially become catastrophic. So we had these centrifuge experiments, and then we have the FSSI modeling that we have done, which is fluid soil structure interaction modeling. And you can see here the computed result with, depending on the type of relationship, we have non-macing with friction contact and macing with welded contact, and then the measurements. And we are seeing a very good correspondence between the most representative behavior, which is non-macing with friction contact, with the measured behavior. We're seeing that the hysteretic behavior of the rockfill is very important to capture correctly so that you can reproduce the observations. In this case, the observations are from the centrifuge experiments. Now, I'm going to talk about another problem, but also involves fluid, which is buried reservoirs. This is seismic fluid structure soil interaction of buried reservoirs, which are commonly used in the US as well as elsewhere around the world. So let's talk about the problem. In many parts of the United States, water supply reservoirs in cities are being placed underground on hills so that you can supply water by gravity. And these are built for concrete structures, very large, very wide. They almost have the shape of a pizza box, and they are supported, the vertical load of the roof is supported on columns, and then there's going to be fluid in there, of course, for the water in there. And the question is, how do I estimate the seismic response of these structures? Simplified methods really do not capture. It's not really possible. It's difficult to figure out how to use simplified methods. So that's really difficult. Code-based methods are not applicable. And so really the best way is to have the full soil fluid structure interaction model. In order to do that, we are conducting currently a series of experiments in collaboration with our colleagues at UC Davis, whereby we're going to represent first the fluid and structure interaction, and then soil fluid structure interaction in the centrifuge, and reproduce that in our simulations. And we have gone through the first phase, which is completed, which is the fluid structure interaction. And now we are working on the fluid structure soil interaction, which we hope to start those experiments this month or next month. And this is an example of what you can do in these simulations. We're representing the fluid using an ALE formulation, which provides a better performance in capturing the fluid hydrodynamic response. And the results, in fact, are quite promising and are consistent indeed with the experiments. These simulations are computationally demanding, and so therefore we need to make sure we are able to run them either on small servers, which I have several of which in my office, or in terms of high-performance computing systems. So we have used it on large-scale simulations. We can run very large simulations if we want to, or run a number of uncertainty analyses. These are some comparisons of these compute node specifications, and this is some examples to give you about a feel for how the simulations scale depending on the number of cores. 4, 8, 16, 1-to-1 here. This is speed up is what you desire, but this is difficult to have. The green is the scale up we have seen on our Windows machines versus on HPC machines on Stampede, and you can see at the University of Texas at Austin, and this is really running much faster there. And so we are many of our simulations, we are running them on these platforms. Well, that leads me now to our conclusions and engineering implications. The advances in analysis software, computing hardware, and big data management tools has enabled a new era in the analysis of complex nonlinear seismic soil structure interaction in 3 dimensions, and I can add to that also fluid. We've demonstrated these successfully for a number of problems: settlements of heavy structures on dense sand, tall building tunnel interaction, soil liquefaction, concrete face rockfill dam, buried water supply reservoirs. Very promising, and I expect that to be the wave of the future. We just need to pay attention to the computational needs and costs, but we gain insights that are very difficult to gain using simplified decoupled simulations or simplified 2D analyses. Probably many of you would be interested in some of the tools we are using, and we are very delighted to make them available to the community. The iSoil model, which runs efficiently within LS-DYNA, can be made available to you upon request. We're going to make it available through a GitLab platform. You will have to have your own LS-DYNA license, of course. Feel free to contact me, and I'm happy to provide you with this material. With that, thank you very much. 감사합니다, and I'm very happy to take any questions.